Today we're doing just how do you solve a three-dimensional system of equations. So a system where you have three variables and three unknowns, or three variables and or three equations and three unknowns, which is the only way you can really solve it. Or you can have three equations. You can have two equations and three unknowns, in which case you can't really solve it, right? Or you can have infinite solutions or something like that. Or and we'll talk about one of those in a minute. Okay. So if you have three equations, what does that say? If they say solve, and it's not the most exciting thing in the world, but it's kind of fun and mechanical. X minus y or x minus y plus 2z, and then we have y plus z, whoops, I forgot to make it equals 1. Y, what the heck am I writing? Y plus z equals 3. Z equals 3, and z equals 2. Z equals 2. Okay? This is called the multivariable system in row echelon form. And an echelon, it's kind of like, you know how geese fly, they kind of fly in an echelon with the first guy going first. And so notice that there's three terms in the first equation, two terms in the second equation, and one term in the last equation. And it's easy to solve this system, right? Just by substitution, right? Because you already know what z is, right? So you just take z and plug it in there over here. And then you get y equals what? Y equals 1. And now that you know z and y, you can plug those in to the next equation. So you plug in 2 in here, and you plug in 1 in here, and you would get x minus 1 plus 4 equals 1. So x plus 3 equals 1. So x equals -2. So we know z, we know y. And you want to write it as an ordered triple with x going first, -2, 1, and 2, like this. And this is called an ordered triple. Okay? And what are you doing when you solve this system? It has different applications, but graphically, something with like x minus y plus 2z equals 1, that makes a plane, okay? And at y plus z equals 3 also makes a plane, as does z equals 2. It's parallel to the z axis, okay? And so what you're finding when you're finding these solutions, you're finding where those three planes intersect, okay, at a specific point, which doesn't occur that frequently. I'll bring up a picture after I teach you a little bit. But see how easy that is to solve? That's easy because it's in this row echelon form. Now, they will hardly ever be in that form originally, so your goal when you're solving a 3D system is to get them into that form, so it makes it easier to solve, okay? So, for instance, then they have this thing called gaussian elimination, okay? And so Gaussian elimination is, I hope I spelled that right. Gaussian elimination is the process of it's transforming. I should write a different code. Transforming a system into row echelon form. interchanging equations. Interchanging equations. And you'll see what I mean in a minute. Or 2 is multiplying by a constant. Is it multiplying by a constant? Right, a constant. And 3 is adding or subtracting a multiple of one equation to another. Okay? So, for instance, they'll give you something that looks like this, and I try not to pick the exact same examples that are in your book. X minus 3y. It is. I'm going to show you where this, where we got that original one that was in row echelon form. So I notice this equation is the same as that first one. And then we have another equation, 2x minus 5y plus z equals negative 5, and 3x plus y minus 2z equals negative 1. And they say solve this using Gaussian elimination. Okay? So you may have you solved three-dimensional systems before, or three systems? And probably what you were told to do is like get rid of the z's in one, right? Get rid of the z's in two equations, or the y's or something like that, and then use those two equations and solve that next system of equations. Yes? No? Well, you can still use that method, but this is kind of a specific method that you want to try to do. So what you do is you leave this first one alone, and you try to get these two just in terms of you try to eliminate the x's first. Okay. So what I'm going to do is look at these two equations up here. How can I get rid of the x's up there? What would I have to multiply that top equation by? Negative 2. So I'm going to multiply that top equation by negative 2. And you guys are pretty good at math and stuff, so I'm not going to do the multiplication because is that what I did? That's what did I get rid of the first time? So I want to make sure I have this right. X minus 3y. Yeah. So first I'm going to multiply that top one by negative 2. So if I multiply that top one by negative 2, first I leave this top one alone. Okay? X minus 3y plus 2z equals 1. And then I'm going to add these two equations, this one multiplied by 2, and this one left alone by itself. So do you guys see that the two x's cancel out? Then I get negative 2 times 3y makes positive 6y minus 5y gives you what? How many y's? No, because it's plus 6 and minus 5. 1y. So I have 1y there. And then I have minus 2 times plus 2 is minus 4, negative 3z. And then you can't forget about the constant. Negative 2 plus negative 5 makes negative 7, okay? And I'm trying to save space. Do you guys see what I did there? Yeah, most of you. So then I want to find some way to use this equation to get rid of the x's in this equation. So I'm going to erase this for a minute, okay? And what would I need to multiply this equation by to get rid of the x's with this one? If I come negative 3. So now I'm going to multiply this one by negative 3 and add those two together. See what I did? Okay. So I have negative 3x, positive 3x disappears, and I get positive 9y and positive 1y, which makes 10y. Let me make sure I'm doing this right. Okay, that's right, 10y. And then I have negative 3 times this makes negative 6z plus, whoops, I'm looking at this one. Negative 6z and minus 2z makes no, because it's positive 9, right? Negative times a negative. Minus 8z equals negative 3 times 1 makes negative 3, and negative 3 plus negative 1 makes negative 4. Right? Did I do that right? I think I did that right. Okay? So now, what I'm going to do, I'm going to do the same thing, except I'm going to get rid of the y's in these two equations. How can I get rid of the y's in one of those two equations? What could I multiply 1 by? What could I multiply this equation by? Negative 10. So I'm going to take this one. So here's my new system, which is equivalent to that last system, and I'm going to multiply this one by negative 10 to make the y's go away from those two equations, and I'm going to leave that same one, x minus 3y plus 2z equals 1. I'm going to leave this one as y minus 3z equals negative 7. And then I'm going to add negative 10 times this plus this, which makes the y's go away. Negative 10 times positive 3, negative 3 is positive 30 minus 8 makes 22z. 22z. And negative 10 times negative 7 makes positive 70 minus 4 makes 66, right? So now I'm just about done, because now I can solve this system. What's z equal to? Z equals 3, right? By dividing that. And then I can take 3 and plug it in here. So I get y minus 3 times 3 equals negative 7. So y equals positive 2, right? Y equals 2, because that's negative 9 added both sides. And so now I go up here, and I get x minus 3 times 2 plus 2 times 3 equals 1, which gives me x minus 6 plus 6 equals 1, so x equals 1. So my answer as an order pair is 1, 2, 3. Okay? It's kind of tricky, but so if it helps you, you can rewrite. I just didn't want to keep rewriting my equations, so you could have rewritten this as 3 times this, but you want to leave this one alone, and then you want to leave this one alone. So notice this was my original equation. This is my when I got rid of the x's, and this is when I got rid of the z's. Yeah? No, it's kind of tricky. Have any of you ever done that before? No. What time do we get out? 10:05? 10:10? 10:10. Okay, I'm good. Okay, so let's try. Do you guys want to try one? So maybe you should try. You like it? Who likes doing this? It's kind of fun. Gaussian, I guess I should capitalize it because he's a famous math person. Elimination. We'll give you another shot. Okay? To solve. Uh-oh, Moby's gonna. We'll do another one. Don't worry. X plus 3y. x plus 3y minus 2z equals 1. And then we have negative x plus 2y plus 6z equals negative 2. And then we have 3x plus 11y plus 2z equals 6. So, okay, so who can tell me what I should do first? You can do it. Easy. Yeah, good. Write the first equation again. X plus 3y minus 2z equals 1. Now what, Zachy?
Since you don't really need to do anything with the
Good. Just add these two together, right? See that? Because you want to make the x's go away. Here. Okay, so we're just going to add these together. Gives me what? Plus 4z. I always meant be careful, you mess up. Equals negative 1. And then what? Good. Multiply the top one by a negative 3, right? And combine it with that one. Get rid of the x's, right? So that's going to be, what's that, negative 9 and positive 11 makes negative 2y? Plus 2y? Right. Plus 2y. And plus 6z plus 2z. Is that 11z?
8z.
I knew that. I was just testing to see if you guys were paying attention. Okay? And then negative 3 and 6 makes 3. Okay? So far I have this. Now I'm going to rewrite just like I did before. So this is going to go to x plus 3y minus 2z equals 1. And then this is going to stay as 5y. I've never done this before. It's fun. Should 4z. Well, because it gives you a nice method for doing it. You know, before I could always like multiply by this, and that by that, and it's kind of random what I was doing. But this gives you a nice straightforward method. So now what? What should I multiply by what?
Negative 2 for the middle.
Good. Multiply. Oh, no. You could solve, but you want to get the z, right? You want to get the z, so you don't want to get the y. So what do I do? You can get the y, but
It'd be easier to get the y.
yeah, but they want it in row echelon form, meaning the z needs to come at the end. So you want to get rid of, so row echelon form, it needs to go first get rid of the x's, then you get rid of the y's, and then you have z. You could do that, you know, but it wouldn't be like really Gaussian elimination. So I'm going to multiply this one by this. Oh, by 2/5.
Yeah.
Ooh.
No, you have to do 2/5 to get rid
No.
of the y.
Wait. I want to get rid of half by. Is that what I did? Hold on. I can't be stymied here wrong. That's my problem. This should have been a negative sign to begin with. Okay. Let's just. Can we do that? Is that going to mess me all up? Okay, so we could do that. Multiply this equation by
2, and then the one you're
2, and this one by negative 5.
Oh yeah.
Okay. And then what that gives me, 10 and 10 disappear, and 8 and negative 40, right? 8 and negative 40 makes what? Negative 32 z, and negative 2 and negative 15 makes negative 17. Negative 17. And then you get some ugly looking thing for z, right? Which would have worked if this were the system, and then you could get one. But the reason I chose this one, which didn't work, which when I wrote it down, you would have gotten, if you did it with this being a minus sign over here, you would have got something like 0 equals 5, which means what?
No solution.
No solution. Okay, so just like when you have a system of linear equations, if you get something like 0 equals 5, it means no solution. And in the book, they go into the various types of no solutions that you can have. But here, we're not going to worry about that, okay? Because I'll show you a picture of different types of no solution. And then you could also have something like, if you have 5 equals 5, what does that mean?
Infinite.
Infinite solution. So if you end up with something like this, just like with that system of two equations, no solutions, 5 equals 5, you have infinite solutions, okay? And as long as I have it up, I'm going to open up to show you. It's in your book, but I think I made a copy of it. File open, hopefully pre-calc chapter 6. Pre-calc 13. Where's I can't find it. Pre-calc. Maybe I have to do this. Maybe I should pause first. It's from your book, okay? And I just kind of wanted to show you some things about these three-dimensional systems. It's kind of hard to see, but you can look in your book if you want to. But what did that do? Just made nothing really. But what you can see is that if 3 planes intersect at a point, that means you have one solution, okay? If 3 planes, this is actually, how many planes is that? 1, 2, 3. This is no solution because they can intersect at a line, like that. So you can come up with equations of these lines, but we're not going to worry about it in this class, okay? They can be parallel planes, in which case you would have no solution. They can intersect. This is said to have a solution, but it would be infinite solutions. So this is the only case in which you have infinite solutions, in which your 3 planes intersect at a line. Yes? Okay? And then you could have one solution if all 3 of the planes are disguised as in a different form. Now the other thing, if you're interested in how do I graph one of these equations, okay, like they have up here 3x plus 2y plus 4z equals 12. The way that they do that is they plug in, they set two of the variables equal. So the xy plane looks like this: x going this way, y going this way, and xyz plane, 3-dimensional plane, going that way, and negative y would be this way, and negative x would be this way, and negative z would be down. So just like if you're graphing like an equation in standard form, like ax plus by equals c, what you would do is take 2 of the variables and set them equal to 0. So if x is 0 and y is 0, then z would have to be what up here? If x is 0 and y is 0, z would have to be 3. And that's this point right there. See that? And then if x is 0 and z is 0, then y would have to be 6. So you put a point at 6, right? And then you put a point at 4 for when y and z are 0. And then you connect those points, and that's the plane that this equation is talking about. Not that we have to actually graph it, but just so you have a sense of what. And if you extended that plane in infinite directions, it's not just this triangle, it actually extends all out everywhere, okay? So that's basically what they're talking about. And then the last thing, I don't have much time, but they also talk about a non-square system, okay? In a non-square system, you end up with something, you come up with the equation of a line. For instance, say you had, so non-square system is when you have more variables than you have equations. X, am I recording? Yes. So x minus 2y plus z equals 2, and 2x minus y minus z equals 1. And if you solve that by Gaussian elimination, you end up getting x, if I get it out, x minus 2y, this one is in your book, plus z equals 2, and then y minus z equals negative 1, and that's all you get. And so you get y equals z plus 1, which is the equation of a line in 3 dimensions. We're not going to worry too much about that, but just if you end up with something like this, that means that the solution to a non-square system is a line, okay? And that would be the equation of a line in the 3-dimensional plane. But you don't have to graph it or anything, you just have to know what it turns out. Y equals z minus 1, right? Should be z minus 1, sorry. Z minus 1. Okay, you want me to write down your homework, or can you look on the website and see what, write it down? Page 499. 499, 1 through 3, 7, 8, 10, 15, 20, 21, 28, I can't read my own writing, 21, 28, 29, 21, 28, 29, and 85. I think that says 29. I'm not sure what this number says. I think that's 29. Okay.